So we're in 15.6, and we're going to talk about surface integrals. And today we're going to talk about surface integrals with scalar fields. We'll extend it to vector fields on Monday. So if we in the last couple of sections, we remember we were talking about a parametric surface. So we have our parametric surface R of u and v. And we said our normal vector. Our normal vector is, we can find a normal vector. So just kind of recapping. A normal vector to the surface at a particular point is, we're going to say n equals r sub u cross r sub v. So that gave us a normal vector. And our surface area, or surface differential, a little piece of surface area, that ds was, for a parametric surface, was the magnitude of this cross product. We approximated the area of a little parallelogram with the magnitude of the cross product. So that was our surface area differential. And we said the surface area S was the double integral over our region, whatever region this surface is above in the UV plane, was the double integral of this magnitude of this cross product. And R is our region in the UV plane. So what I want to do is relate this to how we defined the line integral of a scalar field. So a line integral of f of xy ds, we said we could evaluate this because ds was the magnitude of r prime dt. We could evaluate this line integral as a normal integral, a to b, and we're going to represent f, we're going to parameterize our curve c, represent f in terms of the parameters, and then our ds was the magnitude of r prime dt. So this gave us a way to evaluate this scalar line integral. And we use this to find the mass of a wire, the lateral surface area above our curve and below the surface. So a couple of ways that we interpreted this line integral. And this was how we evaluated this scalar line integral. We represent f in terms of our parameterization of the curve, and ds was r prime dt. And the idea was we took f and we multiplied the function value at a particular point times the little increment, the little piece of arc length, and we summed that over the entire curve. We're going to do a similar thing with surface integrals. So we're going to take the value we're going to sum the value of a function at a particular point at the surface, and we're going to multiply that by this ds, the little piece of area on the surface, and we're going to sum that over the surface. Same idea, same exact idea as what we're doing here. So rather than a line integral, we get what we call a surface integral. So I'm going to say, similarly for surfaces, we're going to, again, we're going to take our function value. We're going to have some f of x, y, z. and we're going to multiply it times ds, and we're going to sum this over the surface. And so we're going to define our surface integral. It's going to give us a surface integral. Is the double integral over s of f of x, y, z ds. And the way that we're going to evaluate this is exactly how we evaluated a scalar line integral. This is going to equal the double integral over r of f, and we're going to parameterize our surface, and we're going to express f in terms of our parameterization of the surface. So we're going to say f of r of u and v. And then our ds is the magnitude of ru across r sub v du dv. And again, f is our function expressed in terms of the parameters u and v. ds is this magnitude of the cross product, the u dv, and r is our region in the uv plane. For the most part, we're going to have z is, and I'm going to say if z is some function of x and y, so the way we normally in quotes, normally work with surfaces. So z is some function of x and y. Our ds was this radical, g sub x squared plus g sub y squared plus 1 dy dx. And f of xy then, or sorry, f of xyz just becomes f of x, y, and z is g of x, y. So we just have to substitute for z, and we end up with a function just of x and y. And then r becomes our region in the xy plane. So for the most part, we're going to be working with functions. Z is some function of x and y. This would be our ds, our area, little piece of area, and we represent f of x, y, z. We just have to substitute whatever our function is for z in for our z in the function. So we can think of these surface integrals if we want to give it some kind of physical description. Just like we did for a line integral, if f of x, y, z is a mass per unit area, and we have this surface. So if we sum the mass per unit area of ds over the surface, we would get the mass of whatever it is that's making up this surface. We could think of f of x, y, z as charge per unit area, and we're summing the charge per unit area over the surface. That would give us the charge on the entire surface. So there's lots of ways we can interpret a surface integral. The physical interpretations depends on what f of x, y, z is and what we're saying our surface represents. So in the abstract, we're just taking that function value and multiplying it by the area at that particular point, and we're summing that over the entire surface. All right, everyone good with what a surface integral is? So what I want to do next is just work on evaluating, setting up and evaluating some of these surface integrals. Surface integrals can be a little bit tricky, not necessarily difficult, but they can be difficult, tricky to set up. What we're going to do with the surface integrals, just like we did with line integrals, is we're going to move from a scalar surface integral, which is what we have here, to a vector surface integral. And what we'll be interested in with our vector surface integrals is we will sum the normal component of a field over the surface. So we'll be interested in the normal component of the field at a particular point at each point on the surface, and we're going to sum that normal component over the surface. All right. Questions before we move on? I always liked surface integrals. How was the phrase, just the phrase surface integral? Doesn't that sound, it just has a nice ring to it, surface integral. Line integral, it's kind of, line is not that exciting, but you type surface integral, that sounds like you're really saying something. All right. So let's look at a couple of examples, and then the last example we'll do is one of my favorite examples because it brings in a lot of different stuff that we've talked about over the course of the semester. All right. We want to evaluate the surface integral x minus 2y plus z ds. And where S, our surface, is z equals 15 minus 2x plus 3y, for 0 less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 4. So before we set this up, let's talk about what we're doing here. So this surface z equals 15 minus 2x plus 3y. What is that surface? Plane, right? So we have a plane. So our surface is a plane. And the region, the xy plane. 0 less than or equal to x less than or equal to 2. 0 less than or equal to y less than or equal to 4. What is that region? Rectangle. So our region in the xy plane is a rectangle. So this is not going to be a tough one to set up, because our region is a nice simple region. Our boundaries in the xy plane are just constants, and our surface is a plane, and our function is a pretty nice function. All right. So here we have z equals g of xy. We have a nice surface. We don't have to worry about our magnitude of our cross product, so we just need to find our partial derivatives. So g sub x, a partial derivative with respect to x, is just negative 2, and g sub y is just 3. So our ds, our little area element, is going to be negative 2 squared plus 3 squared plus 1. And we just end up with dy dx, and we end up with just the square root of 14 dy dx. And then I want to represent f. This is f of xyz. Represent f in terms of the surface. So we're going to say f of xyz is x minus 2y plus z, and I'm going to substitute this in for z. When I substitute that in for z, I get that this equals minus x plus y plus 15. So I'm just substituting this for z. So our integral, nice easy integral for this first one. So we have the integral from 0 to 4, the integral from 0 to 2 of minus x plus y plus 15 times the square root of 14 dy dx. Nice easy evaluation. Double integral. This is not a tough double integral to evaluate at all. When we evaluate this, we get 128 times the square root of 14. Did I do it the other way around? So dx. So yeah, the way I set it up would be dx dy. Or I could switch those two around. I don't know why I did dx dy this time. Normally I do dy dx. So this one, nice easy surface integral to evaluate. So if this plane, if we're talking about a plane, and this gives us the charge per unit area on the plane, this would be the total charge on the plane over this region. Would be a way we can interpret that. If this were, let's say this were the plane represented a piece of plywood, and this was the mass per unit area as a function of x, y, and z, this would be the total mass of that piece of plywood over this region in the xy plane. Different ways to interpret it. So probably not normal to define the mass of a piece of plywood in terms of x, y, and z over a particular region. And usually the mass of a plywood is probably not going to vary that much as we move around in the x, y, and z. Pretty strange piece of plywood. All right, questions there? All right, let's look at another example. So this one we'll talk about a parametric surface. So we want to evaluate our surface integral S, f of x, y, ds. I just want to state these questions in the different ways that you'll see them. So for this one, we're going to say f of x, y is x plus y. So our function's nice and easy. But our surface, this time our surface is given by a parametric surface. Our u and v is 2 cosine u I hat plus 2 sine u j hat plus v k hat, where 0 less than or equal to u less than or equal to pi over 2, and v is between 0 and 2. Before we set up our integral, what is this surface? Cylinder. So we have x squared plus y squared equals 4. And z can be anything. So we have a circle in the xy plane for any z. So we have a cylinder about the z-axis, and we're going from 0 to pi over 2, and v is going from 0 to 2. So 0 to pi over 2 is going to keep us in the first octant. So we have a little wedge shape going up along the z-axis with a height of 2. It's nice to be able to visualize the surface that we're talking about before we set it up. All right, so since we have a parametric surface, we need to form our cross product, take the magnitude of our cross product, and we're going to integrate that our ds is going to be the magnitude of our cross product, and then we're going to represent our function in terms of the parameters. So let's do our partial derivatives. R sub u, not difficult partial derivatives. So we get a minus 2 sine u I hat plus 2 cosine u j hat. And R sub b, take our partial derivative, we just end up with 1 k hat. The nice thing about one nice thing about these problems, one thing that I like about these problems is we end up doing so much of what we've done all semester in one problem. So we're taking partial derivatives, we're talking about surfaces, we're doing cross products, we're doing multiple integrals. We might talk about different coordinate systems. When we start doing vector surface integrals, we'll be talking about normal vectors. We'll be talking about the gradient. So all of these things start coming together in a single problem. All right, let's do our cross product. So what's interesting to me is we end up doing something that was an entire problem before. Thinking about what this surface is just part of one problem. Finding a cross product would be one problem that we would do. Now it's part of doing another problem. Partial derivatives, one problem. Now it's part of a bigger problem. Kind of like that. So this is I hat, j hat, k hat. I always write my determinant out. This is cosine u, and this is a 0, and a 0, 0, 1. And I end up with, when I do this, when I form my cross product, I get 2 cosine u I hat plus 2 sine u j hat. And the magnitude of this cross product comes out to be 2. So that didn't add much complication to our integral, and we need to write f of x and y in terms of our parameters. So f of xy equals x, which is 2 cosine u, and plus y plus 2 sine u. And now we're all set to evaluate our integral. So we have the integral from 0 to pi over 2, the integral from 0 to 2 of 2 cosine u plus 2 sine u times 2, and this would be dv du. Nice easy integrals to evaluate, or double integrals, easy to evaluate. We end up with, when we evaluate this, we end up with 16. So not too bad here, not too bad. Next one will take a little more work. So questions here? All right. This is my favorite surface integral, I think, that we do. I always like it when we get to this example. I look forward to it every year. So we're going to evaluate the integral, surface integral, f of x, y, z, ds. And for this example, f of x, y, z is the square root of x squared plus y squared plus z squared. So this is looking a little more challenging already. And our surface is z equals the square root of x squared plus y squared. And we're saying that x minus 1 squared plus y squared is less than or equal to 1. So before we start to set this up, what does the format of the function and the surface, what does that suggest that we're going to be looking at? What was it? Polar. We're probably going to be looking at polar coordinates because we have these x squareds, y squareds, z squareds, and these radicals. So we're probably going to be looking at polar coordinates. So just the form of the problem suggests polar coordinates. So I'm going to say I'm just going to put a question mark. So just looking at that, I think we're going to need polar coordinates. let's think about what this problem is asking us. Our surface, it's saying z equals the square root of x squared plus y squared. What kind of surface is that? If y is 0, if we're looking at just in the xz plane, z equals the square root of x squared. So z equals x, which is a line. Same thing in the, if x equals 0 in the yz plane, we get z equals y. We get a line in the yz plane. So what kind of surface? It's a cone. So we're talking about a cone. So our surface is a cone. What is this telling us? X squared, x minus 1 squared plus y squared is less than or equal to 1. Why do we need that in there? This is a circle. So what is this circle telling us? That's our region in the xy plane. So our surface is a cone. Our region, we're looking at the region in the xy plane that's bounded by this circle. So we have a cone. So we have a cone above a circle in the xy plane. So this problem adds a little wrinkle to this, because usually when we're talking about cones, we just talk about the portion of the cone if z was, for z less than 4. So we're talking about the cone, because our cone is centered on the z-axis, we talk about just a circle that's centered about the origin. Here we're saying the portion of this cone that's above this circle in the xy plane. So this gives us our region in the xy plane. So that adds another little thing we have to deal with in our problem. So this gives us our surface. This gives us our region in the xy plane. So we need to, because we don't have a parametric surface, we have a nice z equals f of xy. We need to just form our partial derivatives to find our ds. So dz dx. When we take a partial derivative, we've done this, we've looked at this partial derivative before a fair number of times. We get x over square root of x squared plus y squared, and dz dy, partial with respect to y, is y over the square root of x squared plus y squared. And our ds is the square root of this quantity, x over, x. I'm going to write it, so we're squaring this, x squared over x squared plus y squared plus y squared over x squared plus y squared plus 1 dy dx. Do we remember what this simplifies to? What is it? Square root of 2. So we find a common denominator, and we end up with the x squared plus y squareds cancel, and we just end up with a 1 plus 1, and this simplifies to square root of 2. So that's not too bad. So this, our ds turns out not too bad. We need to express f in terms of our surface. So we're going to substitute z equals the square root of x squared plus y squared in here, and we get that f equals x squared plus y squared plus x squared plus y squared. We get 2x squared plus y squared. And we end up with a square root of 2 times the square root of x squared plus y squared. So our double integral that we're going to evaluate is the double integral over our region in the xy plane of 2. We have a square root of 2 and a square root of 2. Square root of x squared plus y squared dy dx. Now we need to figure out our region in the xy plane. Our region is this circle in the xy plane. So here's where we're going to move to polar coordinates. So we need to, in order to evaluate this double integral, we need to come up with our region in the xy plane, given by this circle. Is everybody with me so far? There's a lot going on with this problem. So this setup not too bad. Now we need to find our region. So I'm going to go to our page, next page here. So our region in the xy plane. We said we have this circle, x minus 1 squared plus y squared less than or equal to 1. We're going to use polar coordinates. This is where we're going to use polar coordinates. So we can take our question mark away here, and I'm going to say exclamation point, because we are using polar coordinates. X equals r cosine theta, and y equals r sine theta. And I'm just going to plug these in to this region to get a polar representation of our region. So we have r cosine theta minus 1. And if you're familiar, if you have some familiarity with polar curves, you might see where this is going to lead to. Plus r squared sine squared theta less than or equal to 1. So this circle, before we go on, this circle is, where's our center? 1, 0, so it's on the x-axis. Our radius is 1, so we need a circle with radius 1 on the x-axis. Does anybody remember what the polar equation of a circle on the x-axis radius 1 is? R equals 2 cosine theta. That's where we're going to end up here. Sine squared, yes. Thank you. So we're going to end up with an r equals 2 cosine theta. But let's go through the process. If we didn't remember that was the polar equation of a circle with center 1, 0, radius 1. So we're going to square this out. So we end up with r squared cosine squared theta minus 2r cosine theta plus r squared sine squared theta plus 1. There's a plus 1 there. Less than or equal to 1. Combine our like terms, and we get r squared cosine squared theta plus r squared sine squared theta. We can factor out that cosine squared and sine squared, and we just end up with an r squared. R squared minus 2 r cosine theta, and we can subtract the 1, and we get less than or equal to 0. And then we can factor here. We get r times r minus 2 cosine theta. There's our 2 cosine theta, less than or equal to 0. We are not worried about when r equals 0. We're going to ignore the r equals 0 solution for that. So r is finally less than or equal to 2 cosine theta. So our region in the in the xy plane is this circle r is less than or equal to 2 cosine theta. So now we can substitute. Now we can substitute our polar coordinates. Our circle, the boundary in the region in the xy plane is this circle. Our circle is traced once when theta varies from what to what? Circle is traced once from 0 to pi. Cosine of theta, cosine of 0 is 1, and cosine of pi is -1. So this is going to be traced once from 0 to pi. So if we're at the point in polar coordinates, where we're at the point, if theta equals 0, we're at the point 2, 0, and if theta equals pi, our radius is -2. So when we go to pi, -2, we're back to the same point. So that takes us around 1/10. Traced once from 0 to pi. So that gives us our boundary, our limits for our theta. So finally, our integral, our double integral, is the integral from, we had 2, back up here really quickly, was 2 square root of x squared plus y squared dy dx. We're going to change that to polar coordinates. So 2, theta is going from 0 to pi. Our radius is going from 0 to 2 cosine theta. X squared of x squared plus y squared is r. And then in polar coordinates we have an r dr d theta. So that's our integral. So now we need to evaluate this. Doesn't look too bad, does it? Okay. Everybody good so far? This problem is taking a lot of work. That's one reason I like it. All kinds of different stuff happening here. All right, so let's evaluate this integral. So I'm going to go to another page and we'll evaluate this integral. So we have 2, the integral from 0 to pi, the integral from 0 to 2 cosine theta of r squared dr d theta. So we're going to evaluate this. We get 2/3, integral from 0 to pi of r cubed, evaluated from 0 to 2 cosine theta d theta. And when we evaluate that, we get 16/3, the integral from 0 to pi of cosine cubed theta d theta. Now we need to think about this. Cosine cubed. The period of cosine cubed is 2 pi. If we evaluate this this function over half a period, a cosine function over half a period, what's going to happen? Here's a cosine function, and here's half a period. If we evaluate this integral over half a period, what would happen? We'd get 0. For this surface integral, does it make sense that this surface integral would evaluate to 0? Let me go clear back here. F of x, y, z, is f of x, y, z ever negative? No. It's always positive. Our surface is a cone above the xy plane. ds is a little element of area on that cone. Is that ever going to be negative? No. So we're summing a positive function times a piece of area. Does it make sense that we could get a zero surface integral? Can't come out to zero. Now sometimes it does make sense. It could make sense for a surface integral to come out to zero if we were saying that, so say we were summing the charges and some were positive and some were negative. We wanted the total charge. It could come out to zero. Sometimes our line integral comes out to zero because we're talking about the work done. So it can make sense for integrals to evaluate to zero, but in this particular situation it doesn't. So if we kept going from here, we'd end up with our integral evaluating to zero. So what do we need to do? Divide our region in half and multiply the result by 2. So we don't want this to come out to zero, because if we evaluate this as is, we'd come out to zero. And we would have done all of that work, all these, how many pages? We have 2 pages here now on the screen to come out to zero. And we'd end up with the wrong answer. So we're going to divide this in half. So this is going to be 32 thirds. We're going to multiply this by 2. 32 thirds, the integral from 0 to pi over 2 cosine cubed theta d theta. Now we solve that problem. Our last problem, how do we integrate cosine cubed? So our calculator will probably do it, but since we're almost graduating, we're really smart, we want to not use our calculator, right? We want to be as smart as Stephen Wolfram and Wolfram Alpha this ourselves. Any idea? U sub? What's our U? And what's our du? So Brady says cosine squared. So we're on the right track there. I'm going to go over here. There we go. So Jacob says we're going to separate this into a cosine times a cosine squared. So this is 32 thirds, integral from 0 to pi over 2 of cosine theta times cosine squared theta d theta. And then this cosine squared theta, I'm going to rewrite that as 32 thirds, integral from 0 to pi over 2 of cosine theta times 1 minus sine squared theta d theta. And now we have a u sub. We have one integral that's just cosine theta d theta. The other integral is negative sine squared theta times cosine theta. Our u is sine theta, and our du is cosine theta d theta. So now we can evaluate this. This is 32 thirds. This is evaluates to sine theta minus sine cubed theta over 3. And we're evaluating that on 0 to pi over 2. And be careful, this is a common mistake that people make with these kinds of integrals. We can end up with a value, not for this particular one, but a lot of times with trig integrals and with exponential integrals, we can get a value for the lower limit. So this particular one doesn't give us a value, but be careful with these. Trig integrals and exponential integrals, we can end up with a value at the lower limit. We evaluate this, and this comes out nicely. We get 64 ninths. Finally. What an awesome problem this one. We dealt with partial derivatives. We had to simplify this ugly radical. We had to find our region in the xy plane. We had to figure out our boundaries for theta. Then we had to evaluate this nice integral. love this problem. Monday, when I realized we were going to do this section today, I was so excited all week that we got to do this problem today. This is my favorite surface integral problem. All right, questions there? Okay. And we all hope that not all of our homework problems are like this, right? Okay. Oh, we don't get many homework assignments like this.